Alright, so this next video we're talking about the behaviors of light, the things that light does to help us to see what it really is. So you need to understand that there's been a debate for a long time actually of what light really is. Some people thought light was a wave, some people thought it was a particle. Well, it turns out it's actually both. It can behave as a wave and it can behave as a particle. In much a similar way, when I'm here at home, my kids call me Dad. When I'm there at school, you guys call me Mr. Vols. Well, just because I have two different names doesn't mean I'm two different people. It's that if you see me in two different places, I might look a little different. Like I probably don't look right now like you've ever seen me at school. I'm wearing shorts and a t-shirt. Typically don't teach in that kind of stuff. But I'm the same person, and light is the same way. Light simply can behave as a wave in some circumstances and some things that ways that we observe it. And in other ways it can behave as a particle. So there are 5 wave behaviors we're going to talk about. There are 2 specific particle behaviors that we're going to talk about. Let's look at the wave behaviors first. So these are the things that light does that prove to us that light indeed is a wave, right? 5 wave behaviors, and they are reflection, refraction, diffraction, interference, and polarization. You say that 5 times fast. Reflection, refraction, diffraction, interference, and polarization. So we're going to talk about each of these things in turn. In this video, we're probably only going to get through diffraction. So the first wave behavior we'll look at is reflection. Reflection is simply when light bounces off of things, for example in a mirror. This is a wave behavior because all waves do this. I've already showed you reflection with water waves. This is reflection in a mirror. These are the light waves reflecting off a mirror. And even though it looks different, it's the exact same thing happening. These are radio waves sent out by a transmitter, and they go, travel to this plane, to whatever target we're looking at, and they simply bounce off in the other direction. It's reflection. It's reflecting itself. When light comes into a surface, like if this is the surface of the mirror, the way it comes in is the way it comes out. These 2 angles are the same. The color is the same. Everything is the same. That's the reason why you're able to see yourself in the mirror and you look like the person you actually are, because it comes out the way it comes in, very similar to the way a ball bounces off of a surface. So this is reflection. Because light reflects, helps us to know that it's a wave. But that's not a slam dunk, because other things reflect as well. Like I've already said, balls bounce off of surfaces as if they're reflecting. So we have to look at some other things to prove that light is a wave. So the second thing light does to prove that it's a wave is called refraction. Now, refraction is a little bit more complicated. It's when light bends because it changes speed. I mentioned this a little bit in a previous lesson, I think when we talked about waves. Light bends because it changes speed. Now I mentioned when we talked about waves that the speed of a wave is determined by one thing and one thing only, and that is the medium. So if the medium changes, then the speed can change. And it turns out, for a reason that I'm not going to talk about now, that when light changes speed, it actually changes direction. So there's 3 changes here. There's a change in medium, which causes a change in speed, and the change in speed causes the change in direction, or the bending, right? And so there's a lot of things, a lot of ways that we can see refraction. So when you put a pencil in a cup of water, it looks bent or broken. That's because of refraction, because the light is moving through different media here, and it changes speed and therefore changes direction. I've shown you this picture before. This man's head is not actually, or sorry, his body is not actually over here as it looks to your eyes. It's directly under his head, obviously. And it looks that way simply because of refraction, because the light is bending due to a change in speed, which is caused by a change in the medium. Now, refraction can get really exaggerated in some cases, depending on the angle. This is a stick in water. One really interesting example of refraction is bow fishing. Maybe you've been bow fishing before. Bow fishing is pretty complicated because it's easy to miss, and it's easy to miss because your brain kind of fools you. Where you're aiming, if you shoot this arrow here, you find that you actually miss the fish, and there's a reason for that. So when you're bow fishing, you typically use a spotlight. You use a spotlight and you think, okay, I'll shine the light at the fish. and I'll see the fish and I'll be able to shoot straight at the fish. Well, it doesn't work that way. Because the light, to go into the water, it has to change mediums. And when it changes mediums, it changes speed. When it changes speed, it changes direction. That's refraction. So look at this picture. We have lasers shining into water. This is water, this is air. Notice that the lasers are bending. They're changing direction as they get into the water. They no longer travel in the direction where they were traveling before. So this spotlight's going to do the same thing. When it hits the surface of the water right here, it's actually going to bend and it won't even hit the fish. So you find that where you're shining this light, you don't hit the fish at all. So in order to shine the light at the fish, we actually have to point the laser in just a slightly different direction so that it hits the water and bends like the lasers we saw earlier. Now the light gets to the fish. When the light gets to the fish, what we have here is reflection, which is what we talked about a minute ago. That light reflects back off of the fish, back up to the surface of the water, and now the light is going to change mediums again. This point right here went from air into water. Now the light is going to go from water back into air. And very similar to these lasers, when it goes from water back into air, it turns left, or it bends to the left. This light is going to do the same thing. It's going to bend left so that it can actually travel back to your eyes. So the light started here, goes into the water and bends, reflects off the fish and bends again, and you see the fish's reflection here, even though the light started here. Now, the reason why this is a problem is not actually because of the light, it's because of your brain. So your brain doesn't know that this light has bent. All your brain knows is that light travels in straight lines, which makes sense because light typically does. And so what your brain is going to do is it's simply going to trace this light backwards in a straight line, and your brain forms the image of the fish where it thinks it is. And so this is the reason why you tend to shoot too high when you're bow fishing, is you see this image of the fish here, even though the fish is actually at this point. This is all because of refraction. So what's the lesson for bow fishing? Well, you have to aim low. You have to aim low. So wherever you see the fish, you know you see it here, and it's really weird. It feels weird, but you have to actually point your arrow closer to you or lower than the fish actually is. You can see this picture here is a great picture of it. This is taken when the arrow has actually entered into the fish. Here's the fish. And at the point of contact, you can see part of the arrow is out of the water, and it looks like the arrow should just go straight in and actually miss the fish. But at this point here, it bends because the light is bending, and it actually strikes the fish. So you have to aim low because of all this refraction stuff, because light changes direction when it changes mediums. There are lots and lots of different examples of refraction. Lots of different examples. This is one. This is called a water prism. It's simply a triangular prism that's filled with water. And so it makes your face look kind of funky because it bends the light coming from your face. Another example of refraction is a magnifying glass. A lot of physics associated with that we don't need to talk about now. Another example of refraction that I've told you about in a previous lesson is the blurry air above a fire. All the images behind a fire look blurry because the heat changes the medium. And when the medium changes, the air or the light coming through that air bends, and it causes the images behind the fire to look blurry. Diamonds actually take advantage of refraction. This is the reason why diamonds are so valuable and so beautiful. And if you wear glasses take advantage of the phenomenon of refraction to help your brain see a more crisp image. Another really cool example of refraction is this here. Now you might be thinking, hang on, time out, Mr. Valls. We're not talking about Pink Floyd right now. This is physics. Yes. But if you've seen this, of course I know you have. This is the Pink Floyd album. What's that album name? It doesn't matter. It's lost me. This is actually science, because when light bends, the cool thing about refraction is that when this light bends, when it changes mediums, as we've just talked about, it actually splits into its individual colors. So we have white light coming in, but white light contains all of the colors of the rainbow, all of Roy G. Biv. And so when it bends, it splits into its individual colors, and this is the reason why you see rainbows. So this is a picture of an actual prism. When we're shining light into a prism, comes out as a rainbow on the other side. All it's doing is splitting light into all of its individual colors. You can see the red followed by the orange and the yellow and the green, and then the blue-violet end on the far side. They're always in that order. So when you see a rainbow, this is a diagram of what's happening. The sunlight comes through the raindrop. This would be a water droplet in a cloud or in a rainstorm. It changes mediums here. We have refraction, and there's a little bit of spreading out here. Spreads out, it reflects off of the back side of the water drop, comes back to the front, refracts again, we get refraction, and it spreads out a little more, and when it gets to your eyes, the light has been split into its individual colors, into roji biv, so that what your eye is seeing, and it's kind of an optical illusion because it's not really there, your eye is seeing a rainbow. And sometimes you see a double rainbow because instead of just refraction at this point, sometimes we get a little bit of reflection here as well, which causes another rainbow to form in another place, but that's another story for another time. What you need to know is that the reason we see rainbows is because when light bends, it splits into its individual colors. So this proves that light is a wave, right? And the reason this proves that light is a wave is because it takes up three-dimensional space as a wave does. It's not a single particle. Single particles don't do this kind of stuff. So we're getting more of a sense that light is a wave. The third one on this video I want to talk about is diffraction, right? Diffraction is pretty simple. I also talked about diffraction with sound. It's when light spreads out. Well, sound spreads out as well. Remember we talked about Jack is behind the doorway of Jill. Even though he can't see Jill, he can still hear her sound because when it gets beyond the doorway, it bends and it spreads out in all directions. Well, light spreads out too. We can use something called a diffraction grating, which disperses light into its individual component colors. So this is not a prism here. Notice that there is no medium change for this one. All of the stuff before when we were talking about refraction, all of this was medium changes. We got air into water. We were talking about air into glass, air through different kinds of air. That's still a medium change. We got medium changes in all this stuff with refraction. When we talk about diffraction, there is no medium change. This is just a hole in a piece of plastic. When it goes through this hole, it goes, some of that hole blocks out some of the light, and it spreads out or bends as it goes through it. And when light bends, it splits into its individual colors. You might have seen this if you've used diffraction glasses to look at Christmas lights before. These are really cool, really fun. Sometimes they have different shapes, but you can see a whole bunch of little rainbows where you see each of the lights because each light is going through this small hole, this diffraction grating that we call it, causes the light to diffract or spread out. And when it spreads out, it splits into its individual colors. So this is the third wave behavior, diffraction.